let's begin by reviewing the idea of a linear function. You remember this, that if I know some function to be a linear function, right, and it's a linear function, so it is from some vector space to some vector space, correct? So if I know that and I gave you the output of that function to inputs like this, okay, there are 3 inputs because I am showing 3 component vectors. Okay, there are 5, if the inputs are 5 component vectors, I will have to show 5 inputs. That much is clear, right? Right. So if I gave you the outputs of that function to these kinds of inputs, then you will be able to predict what that linear function will do for any input. Do you remember this? And we could show it as a circuit which looks like this. You have, if you have any 3 general numbers, going in, let's say the output is are 2 components for right now. Then there are these multiplier lines, and the multiplier lines have as multipliers the numbers which are these outputs here. You remember this much? Any linear function can be represented in this manner, and anything that's represented in this manner is a linear function. We have done all of this. I am just reviewing what we have done before. So when we think of an inner product, let us say U inner product with X, for a given fixed U, this object is a linear function of the input X. You remember this? For a given fixed U, this object is a linear function of the input X. Why? Because if A times X was presented to it, then the output will become A times. If some X plus W was presented to it, then the output will also add. For a fixed U, correct? And so for a fixed U, this object is a linear function of this input. So if it is a linear function, it must be able to be represented in this fashion, right? So then the question is, what is the representation of this linear function as a function of the argument X in this fashion, as a network? Or that network, you know, you can also call it a matrix, right? You remember this? You don't have to show it like this. I like to show it like this, but you can just show it as a table of numbers. And then you call it a matrix. It's essentially the same thing though. Do you understand the question? How does this function as a function of X, which is a linear function, look like when represented as a network? So first of all, let's see what goes in and what comes out, right? What goes in? With vector notated by X here, so I will say X goes in, right? U doesn't go in because I'm fixing U, right? So if I had to label this object here, I will say that this is the label. U inner product with whatever comes in, okay? I'm kind of inventing a notation to say that, okay? U inner product with whatever is the input, okay? What comes out? A number comes out. But wait, then how can you then talk about linearity? Shouldn't a vector come out? A number is a one-dimensional vector, okay? I wasn't clear about it the day I told you about linearity of inner products, but when you say linearity, both input and output have to be vectors. How are number vectors? Well, they are one-dimensional vector. It's just a one-entry vector, okay? It's a list of numbers with only one entry in the list, okay? So one number comes out. You can think of it as a vector with only one entry, okay? And so, represented as a circuit, how will it look like? First, let's draw it, then we'll worry about what are the numbers, correct? What will it look like? I just want what it looks like. The labels will figure out in a moment. Okay. So how many circles on the top line? Depends on the dimension of x. So whatever is the dimensionality of x, those many input connections, and how many output connections? Just one. Is that okay? And there will be line going from all inputs to all outputs, but it's only one output, so these are all the lines, right? And now what are the numbers on those lines is the next question, okay? How do you find the numbers on that line? You put in specific x's and see what comes out, and that is the number on that line, correct? Right. So, okay, let's assume 4 dimensions just for our example. So now if 1 0 0 goes in, what will come out? The first component of U will come out, agreed? You remember the formula for the inner product, right? It's just multiplying the same index components and then adding all of them up, right? So U inner product x is U1 x1 plus U2 x2 plus U3 x3 plus U4 x4, correct? Where U1, U2, U3, U4 are components of U, x1, x2, x3, x4 are components of x. Now if x was 1 0 0 0, what comes out of this? U1 comes out of this, correct? Right. And so what comes out is just the first entry of U as a vector, okay? And so that is the label we will be giving here, U1, okay? Similarly, if 0 1 0 0 went in, what will come out? U2 will come out, and so that is the multiplier entry I put in here. Similarly, U3 and finally U4. The components of U are the gathering rule, not the spreading rule. The gathering rule of the inner product with U represented as a network. Okay. Now, do you remember, if we wish to tabulate this, how do we tabulate it? The gathering rule is on, gathering rules are on rows. Okay, spreading rules are on columns. That's how you tabulate it. We did this. Go back and review the lecture. This is, and that's just convention. That is just convention. Our convention of how, but it has become a universal convention now. By the way, Russians use the reverse convention, but most textbooks are now using this convention, so we'll follow this convention. So, old Russian textbooks use the reverse convention. You might still find some old like statistics textbooks which use the reverse convention. Okay. So, this will look like this, okay? U1, U2, U3, U4. Okay? Which are the components of the vector U? What are the components of, what is the vector U originally? U is this, U1, U2, U3, U4. Which are the components of the vector U, but put in a row of a table instead of being represented as components of a vector. You can think of this as 4 spreading rules. Remember, spreading rules are in columns. How many spreading rules? As many as there are inputs. So there are 4 spreading rules, each of them has only one number, which means there are 4 columns and every column has only one number. Okay? And it's purely by convention that we choose the spreading rules to be on columns and the gathering rules to be on rows. But we'll remember that convention. Is all of this okay? Okay. It is traditional to call this matrix the transpose of U. Okay, represented as U with a superscript capital T. Okay. Okay. And so, this can now be represented as the linear function, this fellow, operating on the vector, this vector, right? And so, we can write it as U transpose operating on X, okay? By the way, okay, I will say something. The next thing I am going to say for the next 2 minutes will not be in the exam, but I will say it nonetheless, because those of you who have had some linear algebra previously might be already thinking about it or might get confused. There is some reason you could write it like this, okay? And forget that it's a function operating on a vector and just write it like this. And those of you who have done some linear algebra course might actually be used to it looking like this instead of it looking like this. There is some non-trivial mathematical reason why this can be written like this, and we'll not go into it. Okay, but there will be one advanced homework section which will ask you some very advanced details about why this and this are the same, or are they the same, or questions like that. Okay, I'll not discuss it more than this. I will keep on saying that a linear function operated on a vector, and so I'll keep on using operation notation, but a linear algebra book might be doing this instead. Is it okay? So, how does this, the linear operation U transpose U1, U2, U3, U4 operate on the vector x1, x2, x3, x4? How does it do it? And it does it by, you know how it does it, right? If these are x1, x2, x3, x4 going in, what you get is x1 times u1 plus x2 times u2 plus x3 times u3 plus x4 times x4, which is the inner product formula, which is what you want to happen, which is what is happening, which is great. Okay? Right? So, you will get a single number coming out, which is now a vector with a single number in it, which will be the inner product formula. Correct? If I want to do two inner products, okay, so x goes in, and let's say that I want to calculate u comma x and v comma x, where u and v are some two vectors. They are both fixed vectors. You can think of giving x to u comma and separately to v comma. But here is another way you could think of it. Think of a function that takes in a vector and simultaneously calculates its inner product with two vectors. And what will it output then? It will have to output two numbers, right? One for u, one for v. Thankfully, we already have a data structure to contain two numbers. And what is that? Two entry vectors, right? And so, now think of this as an operation that takes in a vector, takes its inner product with two different vectors and produces two results which are compiled into a single vector. Okay? Will this operation be linear? It's taking in it's taking in a vector, producing another vector, so at least has the chance of being linear. Is it a linear operation? Yeah, right? I mean, you can chase the pluses and scales and see that that works. But another simple way of thinking about it is just draw the network for this. Just draw the network for this. What will be the network for this? One input, it's going to have two outputs now. The numbers on the first lines will be the same. The numbers on the second, so there are now more lines here because another output is being created. Why are the numbers on the first lines the same? Because the first output here is exactly the only output here, or the only output here, correct? inner product with U is the first output here, is the only output here. So this remains the same. And now you have more lines, and what will be the labels on those lines? V1, V2, V3, V4, correct? V1, V2, V3, V4, okay? And so if I were to represent this as a matrix, what will that matrix look like? Write it on in your notebooks. What will this matrix look like? Do you agree? And now this produces two results. The first result is these numbers operating on these numbers producing one answer. The second result is these numbers operating on these numbers producing the second answer, which is exactly what you want to happen. Okay? And so, if I were to like schematically represent this matrix, I would say that this is U transpose on one row and V transpose on a second row. That's what is happening, correct? A U transpose operator concatenated with a V transpose operator. Okay? Write this all down. Now, with this background, we are going to reinterpret what we did in the previous lecture in a slightly new light. I am going to present it as a slightly different mathematical problem, but it is actually the same mathematical problem. Let us say I have three vectors u, v and x. Let us say I have three vectors u, v and x, and I want to find the linear combination of u and v that comes closest to x. I may not have officially used the word linear combination before, so let me explain what that means. Linear combination of u and v is any vector of the form au plus bv, right? Of course, when I am saying all of this, u and v and x have to be compatible, right? They have to have the same number of entries. Otherwise, the question itself doesn't make sense. Okay? The question being asked is, what is the linear combination of u and v, which means for what a and b is au plus bv the closest to the vector x, right? Do you agree that this is just a slightly different way of speaking about the problem that we solved last time? right? When, or at least one of the problems, when we were saying that there is one speaker, there is another speaker, someone is listening to both of them, and what is the unknown scale of both of these that comes closest to what is being heard. Do you remember that? That was in terms of signals. Today we are saying the same thing in terms of vectors, but signals and vectors are interchangeable. So I'm just now going to say the same, almost the same thing in linear algebra terms. Is that okay? So if I have the vector u and I have the vector v, what do all au and bv together form? They form a plane, right? Now mind you, this plane might be present in some high dimensional space, but if you just looked at the plane, it will be a plane. We said this before. If you have some vector x, that vector x need not lie in the plane, and you want to find what is the point in the plane that comes closest to x, correct? Yes? Let's call this point something. Let's call it P. Is that okay? I'm going to call this point P. This I will call N. Okay? Now it's linear algebra, so there is no noise, but I can still use any letter. So I'll continue to use N so that I have maximum letters being the same as before. Okay? Here is a question I have. What is P? Mathematically it is, in terms of u and v, it is au plus bv, correct? au plus bv. Okay? For the time being, forget that P is the closest P. For the time being, let us assume that P is allowed to roam around, which means if you take different A's and different B's, you will get different values of the vector P for the time being, okay? Because we are searching in that space to find the best value, which we will eventually find. Can you imagine an operation which takes in A and B and produces P? Can you imagine an operation? So I'll have to go one step back also. For the moment, let P not necessarily be the foot of the perpendicular. P is any point in this plane. Okay. So A and B are changing. As A and B are changing, P is also changing. So we are thinking of any linear combination of of u and v. Okay. So can you imagine an operation which takes in the numbers A and B and produces a corresponding vector P? Is this confusing? Is it okay?
A and B are fixed, right?
No. Let me go back for third time to the previous sentence is important, and that's not just random thing I am saying there. For the moment, P is not necessarily the foot of the perpendicular. P is allowed to roam around on that plane, which means as A and B change, P changes. This was important. So, are A and B fixed? For the moment they are not. Okay? Now, can you imagine an operation that takes in A and B and produces a corresponding P? X is nowhere in the picture, forget X. Hmm? You can imagine it as a network? Draw that network. He thinks he can imagine it as a network. First, let's just imagine it as a black box. What is that? What does that black box look like? Black box or dark green box, because it's a dark green board, not a black board. So, what goes in? But how can A and B go in? Why can't they? So, but how will they go in? As a vector. As a vector. How do you, right? I mean, how do you put in two numbers? When you have a hammer, everything is a nail. So, how do A, B go in? A, B go in by compiling them into a vector. Okay? Correct? And what comes out is the P that corresponds to those particular A, B. So, what goes in is a vector, what comes out is a vector. Then the next question becomes, is this function a linear function? This is now something very new. Is this a linear function with A and B as a vector? We are viewing A and B as a vector for the first time. We thought of them as scalars till now. Okay? So think about it. If A and B became double, will the output P become double? X is nowhere in the picture. Just animate this in your mind. A is the scale of U to use. B is the scale of V to use. If A and B became double, will P become double? Yes, it will. Okay? The other thing is a bit tricky to convince yourself, but yes, that is true as well. Do it yourself. Okay? Superposition. And so this is a linear function, yes. This is a linear function, yes. If this is a linear function, then it is representable as a network. And then what I answered becomes relevant. What is the network that this linear function is? And that network is going to be, now tell me, how many inputs, how many outputs? 2 inputs, 1 output. Correct? Two inputs, 2 outputs. How many outputs? 1 output. Okay, how many for 1?
Yeah, sign of U and B that output.
Yes. Remember, this is a vector coming out. So the number of outputs has to be equal to the number of entries in this vector P.
The number of inputs are also twice.
Hmm?
Also twice. The scale is A and B are
A and B are just numbers, are scalars, that's true. Now being called numbers.
and P are the dimension of U and X. So the output is actually.
Yes, so the output is whatever are the number of dimensions of U and V. Okay? Let's just use 4 for the time being. But this is actually how many are there? As many as the dimensions of U and V and P and X. This is okay. And so there have to be numbers on these lines, correct? What will be the numbers on these lines? Elements of U and elements of V. How do you get that?
That original P can be written as AU1 plus V1.
Okay. Okay. Here's one simple thing, right? Always you ask what are the numbers on these lines. What do? Always put in vectors like 1, 0 and 0, 1 and see what happens. If you put in 1, 0, what happens? U comes out, right? U comes out. So the components of U must be the numbers on these lines. That's it. Correct? And so numbers on this line are U1, U2, U3, U4. Sorry about my font. And the numbers on this line are, these lines are V1, V2, V3, V4. Okay? Right? Now look at this. If 1, 0 went in, what will come out? U1, U2, U3, U4, which is U, correct? If 0, 1 went in, what will come out? V1, V2, V3, V4, which is V. If, let us say, 1, 1 went in, what will come out? U1 plus V1, U2 plus V2, U3 plus V3, U4 plus V4, which is U plus V, the vector, which is what should happen if A is 1 and B is 1. And so forth. Do you see that this network actually implements this operation as an operation from A and B to P? Okay? I'll let you ask questions, just 2 more minutes. Is okay? Now draw it as a table. I never remember what that cross means. Tell me how many columns and how many rows. 4 rows and 2 columns. Okay. Remember that the columns are the spreading rule, rows are the gathering rule. Okay. So now there are 2 spreading rules here. So 2 columns. The first column will be U1, U2, U3, U4. The second column will be V1, V2, V3, V4. Okay? This will operate on your vector AB to produce P, correct? If I were to show this to you schematically, I will say that what has happened here is the U and the V have occurred on columns. Is it okay? Question.
Okay, so the output that we get here, AU1, AU2, AU3, and so on and so forth, that we take the sum of that and it will become P, right?
Yes.
So what if I have another layer and I make another node and take it as a sum of all these outputs?
Okay.
And then, if I remember previously, we can just scale it to have a network of 2 inputs and 1 output.
True. Correct. Yes.
That is possible.
That is possible. Yes.
You can have 1 output.
You could have 1 output. Yes. it will lose information or gain information depending on your point of view. You could do what you just said. Yes, we don't currently have a reason to do it, but if you had a sufficient reason to do that, you could do it. Question.
Components of the variable.
I don't get it. What do you mean?
Let's say U1 we just remove it. And then
Just remove this. Okay.
it will become 0 in terms of
Yeah. Yeah.
counting to come. Otherwise it will become vectors of different.
Yes. Yeah. You are right. I am making no distinction between zero labeled lines and the absence of a line. In my entire presentation throughout this lecture series, I will not make a distinction between zero labeled lines and absent lines.
But technically, like all vectors are infinite dimensional.
Not infinite, but whatever are the input and output sizes, yes. If the signals are infinite dimensional in some application, then yes, there are infinitely many zeros in the network. Yes. So, yeah. I mean, yeah, hand wave your way around that issue. Okay. Coming back. Is this fine? Now I am saying that let me find the P that comes closest. Okay. What will that be now asked as in this new language? When you say find P that comes closest to X, in this new language that we have now set up, what are you asking? What are the values of A and B for which you will get close to P? So for which you will get close to X. Okay. I'm going to call this matrix something. Okay, I'm going to call it Q. Okay. If the vectors U and V are known, then the matrix Q is known. Agreed? And in the problem we are solving, we know U and V as well as X. So we know the matrix Q. Agreed? Let me call A and B something. Let's call it R. Okay. So what was P? What was P can now be called Q operating on R. Correct? Right? Now, the vector R, what are you allowed to do with the vector R? R is nothing but a compilation of A and B. You are allowed to do anything with A and B. You have been asked to come closest, but to come closest, what A and B can you choose? You can choose any A and B. So, which means that you can choose any vector R. Do you understand this? Question? Still? No? Okay. So, what does your question become? Your question becomes, find an R such that QR comes as close to X as possible. Do you understand this? Find an R such that Q operating on R, Q is known because U and V are known. Q operating on R comes as close to X as possible. Right? comes as close, but it may not match exactly. So I am not going to say equal to, comes as close. I'm just this notation for the time being, read it as comes as close as possible. Okay. Question. Does R have to be unique? We'll do this informally. What do you think about does R have to be unique? Just from this geometry here. Because every R will take you to a different P, and only one of those P's is going to be the closest. And so it has to be unique. And this is you have to be much more careful than what we just said. But for the time being, it's okay for us to say this. Okay? This is okay? What is QR minus X? Sorry, let's do it the other way around. What is X minus QR? It is N, correct? Agreed? Because this is QR, P is QR. X minus QR is N, correct? Agreed? And now, here we allow ourselves to use the orthogonality principle. The homework will ask you to do this entire derivation that we just did just now without using the orthogonality principle, which means we will prove it even more rigorously. Right now, we'll allow ourselves to use the orthogonality principle, which means we'll allow ourselves to know the geometric fact that this N is perpendicular to this entire plane, right? Which means it's perpendicular to every vector in this plane, right? Right? Which means specifically it's perpendicular to U and V. Do you see it visually that the vector N is perpendicular to U and V? Correct? So what does that mean in our new language? That U transpose operating on N equals 0. V transpose operating on N equals 0. Correct? Correct? Agreed? Let's operate both U transpose and V transpose on N simultaneously. Can you do that? How? How? You think of it like this, right? You take the U transpose on one row, V transpose on another row. This will give you a matrix, right, which is operating, which is taking the inner product with both U and V, correct? So, operating on N equals 0, correct? Is this correct? Okay? I am going to give this a name. If U and V on two columns are called Q, then U transpose and V transpose on two rows should be called Q transpose. Okay? It's a new name. We'll call this Q transpose. Sorry, but by the way, I wrote 0 here. I shouldn't have written 0. That was wrong. What should I have written here? The 0 vector, correct? To be specific, 0, 0. Is okay? What?
N should be a vector.
This. What do you mean by n?
N.
It's a single vector.
Oh. Sorry, I rubbed that entire thing out. The answer is no. That's a good question, and the answer is no. So, see, if you put in nn, then you will be allowed to put in nm, which could be done, but that's a different operation. Okay, here the operation we were specifically looking for is taking in a single, we remember on the previous blackboard, taking in a single vector, operating two inner products on it and producing an output. So that single vector that goes in only once. Okay. Okay. Right? And so this is Q transpose operating on n. Sorry, this, the other bracket is just to compose n. Okay. Q transpose operating on n equals the 0 vector. Is this okay? Okay. But what is the n vector? N vector is x minus qr, correct? And so Q transpose operating on n is going to be Q transpose operating on x minus qr, correct? Is this okay? And so Q transpose operating on x minus qr equals the 0 vector. Is this okay? This is okay? Then what do we do next? Superposition, correct? And so we get Q transpose operating on X equals Q transpose operating on Q operating on R. Is okay? Now on this side something interesting has happened. What has happened? This is a vector being operated upon by a linear operation being further operated upon by another linear operation. But two cascaded linear operations give a linear operation. And what are the numbers in that linear operation? You get them by matrix multiplication, right? So you can think of this as a single operation operating on R. So that matrix is Q transpose Q, correct? Operating on the vector R. Okay? And this is very useful. Why? Okay. Think about Q transpose Q. That is also the case, but so what does it look like? R goes into the matrix Q, and the output of that goes into the matrix Q transpose, correct? So R, this is the matrix Q. So I'll just, R goes into the matrix Q, and that goes into the matrix Q transpose. How many outputs? 2 outputs. Correct? Because the matrix Q transpose takes 2 inner products, so 2 outputs. Correct? Q transpose Q. Remember, by convention, whatever comes later is put before. Okay, this is just operator convention, it's true throughout mathematics. Okay. So if you look at this combined operator, how many inputs and how many outputs? 2 inputs and 2 outputs. Okay, which means that, now look at this very carefully. This is a linear function with 2 inputs and 2 outputs. This R is unknown, we are trying to find it because that's A and B which we are trying to find. On the other side here we have Q transpose, which is a linear function operating on X, which is a known vector. Both Q transpose and X are known, so that produces a vector. So you have a vector equals a known matrix operating on an unknown vector. And that known matrix has as many rows as columns, which means as many outputs as inputs, which means that this is a like a linear system of equations that you can solve. Do you understand this? Now, here I will use linear algebra notation and say that that solution, how many of you have studied linear algebra? It's a compulsory course. Okay, I'll happily use linear algebra notation then. Till now I have tried to avoid it, but it would take me 2 more lectures to be able to do this formally, so I'll use linear algebra notation. Since it's as many rows as columns matrix, that matrix has an inverse, which is also a matrix. This requires proof actually, that the inverse of a linear function is a linear function, requires proof. We'll use it without proof right now. Q transpose Q inverse operating on Q transpose operating on X is R. Okay. Now you can, now think about it, think about this. Q transpose is a linear function. Okay. Q transpose Q inverse is a linear function. So this is 2 cascaded linear functions, correct? Which means I can collapse them into a single linear function. And so I can write that now as Q transpose Q inverse Q transpose, the linear function operating on X gives me the output I am looking for, R. Is it okay? This thing occurs a lot in all of mathematics, and it's got a special notation for it. People sometimes write it as Q with a superscript dagger, okay, or a sword. This is known by various names. One of the names it's known by is the Moore-Penrose pseudo inverse of Q. Penrose is the Penrose who recently got the Nobel Prize. But this is some work from a long time ago. Moore is even much older than Penrose. Moore did some work in the 1920s, Penrose did some work in the 1950s, and from that this theory came about. Does this make sense? Okay. Let's connect this to what we did last time. Is this okay? And do you understand that this is a solution to the problem of finding the best A and B? Do you realize that? Let's connect this to what we did the last time. This Q transpose is what? Q transpose is U transpose and V transpose on two lines. What is Q? Q is U and V on the columns, right? What will this collapsed matrix look like? For example, what will its first entry be? U transpose U, correct? U transpose U. What will the second entry be? Here, U transpose V. What will this entry be? V transpose U. What will this entry be? V transpose V. Okay? But U transpose U is actually U inner product U, correct? U transpose V is U inner product V. This is V inner product U, this is V inner product V, which are exactly the coefficients of the linear equations that we had last time when we created the orthogonal equations. Remember that? You can go back and look at that lecture. The coefficients of the linear equations from which you find the correct scales are these numbers here. So we have actually not done anything different. It just looks different because we wrote it in linear algebra this time. Okay. There are a few more things to say about this, but we'll say them after a 5-minute break. Break, everyone. So this Q transpose Q is a collapse of the two matrices Q transpose and Q to give a square matrix. Then you take its inverse and then take Q transpose. This gives you a matrix that you can apply on the vector X to produce the best scale of the vectors U and V, which is the best scale of the columns of Q to fit X, to come as close to X as possible, right? This matrix that you are inverting, by the way, someone was asking me, isn't Q transpose Q equal to, isn't Q transpose Q inverse equal to Q inverse Q transpose inverse? And that's important to point out that that is not the case because Q is not a square matrix. Needs to exist, correct. And that's not the case specifically because Q is not a square matrix. The way we are writing it right now, Q is not a square matrix, and so you cannot do that. Okay? Whereas Q transpose Q is a square matrix. Correct? I have been saying this from the last lecture. See, we got as many equations as unknowns. What does that mean? Square matrix. We got a square matrix. That's what makes us happy. That's what you can then use the inversion for, right? Or solution of a linear of solution of a linear of system solution of a system of linear equations for. Thank you. Okay. Some special, sorry, not some special case. Before that, so see when you say Q, so let's try to interpret all of this in the diagram because that's instructive. Q transpose n equals 0. What does that mean? N is perpendicular to U and V, correct? Q transpose X minus QR equals zeros. What does that mean? X minus QR, which is P, the best P, which is this vector, is perpendicular to U and V, right? Find me the P such that this that remains is perpendicular to U and V. Q transpose X equals Q transpose operating on Q operating on R. What does that mean? Or I mean Q operating on R is just P, so just think of it as P for the moment. Q transpose X equals Q transpose P. What does that mean?
The component of X in the plane has this, when it is operated on by Q transpose is the same as P when operated by Q transpose.
Okay. Think of it as follows. So Q transpose X, Q transpose operating on X equals Q transpose operating on P. Think of it column by column. Think of it row by row. This is an equality, which is a vector equality, which is telling you two things. One of those things is that U transpose X equals U transpose P. Right? What is that saying? It is saying that if you projected X onto U and you projected P onto U, you will reach the same point. Do you understand this? Correct? To see that, you should divide by U transpose U. Right? So now this is correct. Remember this. If you divide by U transpose U, now this is the foot of the perpendicular of X onto U. This is the foot of the perpendicular of P onto U. Right? And what you are saying is that X projected onto U and P projected onto U get to the exact same point. And does this make sense? Yes, it makes sense because the difference between them projects to 0 onto U. Do you understand this? This projected onto U will be something, this projected onto U will be something else, but this should project as a 0 onto U. So it shouldn't move the foot of the perpendicular. And so then this projected onto U is the same point. Not evident? Yes. Yes. So So Q transpose X equals Q transpose P means U transpose X equals U transpose P as well as V transpose X equals V transpose P, correct? So I am just trying to explain what U transpose X equals U transpose P means. And to explain that, I divided by U transpose U, which is U comma U, to give you two correlation formulas. And then I am interpreting those correlation formulas to say that X projected onto U and P projected onto U reach the exact same point. That's what this means. Just to get that projection point as a scale of U, you remember that? Yeah, just using that formula, right? And this is something that we are saying without any intervention of V. So, right? Is okay? And similarly, projection of X onto V and P onto V will be the same point of V. Okay? So another way to think of this whole proof is that that's what it is based on. It is based on the fact that X projects onto the U and the V the same as P projects onto U and V. Okay? And that's where you get this formula from. Okay. How will you do this if you had, how will you do this if you had, let us say, 3 vectors UVW, if you had 3 vectors UVW and you were being asked what is the best AU plus BV plus CW, what will you do? Yes. You see, all of that will work. Okay? So, here Q will now have one more column. This R will have one more row. It will be ABC, right? So, you will be taking linear combination of 3 columns. Okay? Orthogonality principle will now say that your error will be perpendicular to U and V and W. That is unvisualizable to us because now the geometry of that object is U and V and W and X, which is 4-dimensional geometry, which is unvisualizable to us. So you are just imagining that that is the truth. Okay? But based on that belief in the orthogonality principle, you get U transpose n equals 0, V transpose n equals 0, W transpose n equals 0, which gives Q transpose n equals 0, 0, 0, which makes the rest of the proof go through as it was before, which gives you this same formula, but the formula looks the same, but it's slightly different because Q now has 3 columns, Q transpose has 3 rows. Okay? So instead of 2 columns and 2 rows, you have 3 columns and 3 rows, which gives this as a 3-row, 3-column matrix, okay, which still has an inverse, and then you will get that inverse and then Q transpose, and that will be still called Q dagger, which will still be the Moore-Penrose Pseudoinverse. That's how you will solve that. Okay? So you could, like mathematically, you could go on adding these vectors. Eventually, the final case will be when you have as many vectors as you have dimensions of your base space itself. Okay? So, for example, if you have a 3-dimensional space and you get U, V, W as vectors in the 3-dimensional space, then what will you be able to do? Any X you will be able to reach it exactly. Correct? Correct? If you have a 10-dimensional space or a 10-component space and you did U, V, W, whatever, alpha, beta, 10 of them, that is the maximum that I can do, because with those many vectors, a linear combination of them can reach any x that you want to reach, right? In that specific case, what will happen? In that specific case, what will happen is that Q itself will have as many rows as columns, okay, which makes Q itself invertible, which then does what? Now you can say that this equals Q inverse Q transpose inverse. Now Q transpose inverse cancels with Q transpose, leaving only Q inverse, which is what should happen. So Q pseudo inverse is equal to Q inverse if Q is a square matrix, which is what should happen. If you have as many vectors as you have dimensions, you can reach any target x that you want to reach precisely, and so the error will be 0. Okay? In practical, yes. So have you heard of this term overfitting? So in practical terms, what happens is that since mathematically just providing more and more approximants is guaranteed to get you closer and closer to whatever is your target, eventually you start creeping into noise. So your A, B's and C's are now actually approximating noise, is what practically starts happening. So you are right in saying that practically there will be some noise, right? So then what does this mean? But you have reached that value exactly. So what happens is that which is being perceived, yes. And even the noise in it was now modeled by you as unknowingly modeled by you as having come out of physical causes, was hallucinated by you, to use a new terminology, as having come out of physical causes. So these are practical considerations. And so while using this practically, if you are trying to actually use it as a data fitting method, you should always use far fewer approximating vectors than you have the dimensionality of your space, practically. If it was 3-dimensional, yes, but my example is 4-dimensional, so still no. But U, V, W, Z, and yes, then you will. By the way, statistics textbook does all of this and gives it a different name. They call it regression, linear regression, multiple linear regression, polynomial regression. Polynomial is also linear regression only. Look at it carefully, okay? Okay. Here's one point. What if U and V were themselves perpendicular to each other? Again, we saw this towards the end of last lecture, but I want to again say that same thing. What if u and v were themselves perpendicular to each other? This is going to become very important for us later on. So, yeah, absolutely. One way to think about that is the off diagonal terms are 0 here, and so then what remained is u transpose u and v transpose v as diagonal terms. What is the inverse of that matrix? Correct, just the reciprocals. Correct, because it's just a matrix. I mean, it's not a matrix, it just takes inputs and then multiplies and produces the same output. As a network, the diagonal matrix is just lines that go like this, correct? And so what is the inverse of that matrix? It's just lines with reciprocals. And so if the off diagonal terms were 0, then the inverse will be the reciprocals 1 upon u transpose u, 1 upon v transpose v, which would give you the correlation formula, right? Because now q transpose q inverse will just be the reciprocals of u transpose u and v transpose v, and then q transpose will operating on x is just going to be u dot x and v dot x. So you just get u dot x upon u dot u and v dot x upon v dot v. Do you understand that? Right? In terms of, geometrically what is happening, if you think about it, if u and v are themselves perpendicular, this is u, this is v, and they are perpendicular to each other, okay? Then if you drop a perpendicular onto u and a perpendicular onto v, then the correct p to use would just be this much of u plus this much of v. This will be true if u and v are perpendicular, right? They are like Cartesian axis basically. And so in that case, you can drop these perpendiculars separately and add them up to get as close to that point as possible. This won't be true if they are not perpendicular. Okay? This will generalize to multiple vectors as well. So you have uv, if you have uvw, what will happen? You will get a 3 by 3 matrix here, but if u and v and w are all perpendicular to each other in pairs, then all the off diagonal terms will be 0, correct? And only u transpose u and v transpose v and w transpose w will be non-zero, and you will take the reciprocals, okay? Yes? So now let's talk about signals again, finally. After doing so much linear algebra, we'll finally come back to talking about signals. Let me say that I have some input signal and I have some output signal, okay? And there is a convolution between these. Okay? And that convolution is with some known impulse response f. Is that okay? Okay. Let me say I know the output. And the question is, what is the input? Of course, when we say we know the output, we always have to assume that there is some added noise to the output. And then the question is, what is the input that I can estimate? Okay? Star f is a known impulse response. Convolution with f, the known impulse response. F is the spreading rule. We can be thinking of this as, I have been given some output, let's call that output x, and I am trying to find that R whose convolution response with a known convolution comes as close to x as possible. Correct? Convolving with a known impulse response f is a linear operation, do you agree? Which means that it is a matrix, do you agree? So, if I were to write this as a matrix, let us say capital F, what will that capital F look like? And let us stick to a picture which looks like this. So, I have 4 numbers to be discovered in R. I have 6 numbers given to me in X, and let us say F has these 3 non-zero numbers on 3 lines. Okay? Let me even just, let us solve it as an example. So, let us give you the numbers. Let us say the numbers are -2, 1 and 6. Okay, since it is convolution, the same numbers are there everywhere, correct? This problem is called the problem of deconvolution, right? If you are given the input and asked to calculate the output, that is convolution. If you are given the output and asked to calculate the input, that is deconvolution, right? Obviously important from the point of view of, if you heard, what might have been said, correct? And this will be important in all sorts of applications. Wherever there is convolution, there is deconvolution, correct? What does the matrix F look like? Now I have given you the numbers. Actually, write down the matrix F. Nice. Then this is the matrix F. Do you agree? How do you write down entries in a matrix? You just put in 1 0 0 0, see what comes out, put that on the first column. You should be used to this by now. Correct? 1 0 0 0, what comes out? -2 1 6 0 0 0. Put that on the first column. 0 1 0 0, put that on the second column, third column, fourth column. This is what you get. Okay? Look at this carefully. This matrix is a matrix with some interesting special structure, isn't it? The -2s are going like this, the 1s are going like this, the 6s are going like this. It doesn't have to be triangular. In fact, it's not triangular. But it has the same numbers going like this diagonally. Why? Which property? Also known as shift invariance, right? Shift invariance is causing those numbers to repeat. Okay. In fact, this whenever you see this in a matrix, that matrix has got a special name. It's called a Toeplitz matrix. Toeplitz. Toeplitz. It's the name of a person. Toeplitz was a German mathematician before the Second World War. Yeah. Okay. Right? And so we are saying what R should this matrix operate on? What R should this matrix operate on to come as close to X as possible, correct? Right? We know the output, yes. Absolutely. Correct. 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 And with all the theory that we developed, we can directly write down the best R to use. Best R to use is what? Is F transpose F inverse F transpose operating on X. Right? This is called the theory of optimal deconvolution. Right? Or if you want, you can think of it as follows. Just think of it as F transpose F R equals F transpose S operating on R equals F transpose X, and you know X, so this vector is known. These numbers here are known because you know F. Only R is unknown. So this is a system of linear equations that you are solving. That's another way to think of it. It's the same thing. The same thing. Either you show it as a system of linear equations or you show it as a matrix formula. Okay? How will you solve this system of linear equations? You must have studied some methods of solving, right? Like Gauss elimination. These are just a square table of coefficients. And I can do Gauss elimination, lower triangle becomes 0, upper triangle becomes 0, only diagonal remains, then you divide, you get the numbers. Remember that? So something as simple as that can be utilized here to get you the best R to use. Okay? The noise that remains will be attributed to the noise that was there in the system, and that noise will be perpendicular to all of these columns. Okay? So that noise will be noise that could have never come out of the convolution. Okay? In what sense?
So let's say we had one more. Now we showed that 3 arrows are coming. Let's say 4 arrows.
Then what will happen?
Yeah, that's what.
So if there was one more non-zero here, what will happen? One more non-zero, one more non-zero. And what will you get? You will get a non-zero entry here and the same number repeating here and here. And either you will have to add a non-zero here, which means you will have to record more data, or then you can do it without recording the extra data. Say that no, I don't have that data, I don't know what to do. What are you going to repeat?
That non-zero.
Yeah, the non-zero term will repeat, but if you don't have the corresponding recording of X, then that's not useful to you. So here we are assuming we have enough of a recording of X and we know the extent of the input. So that is actually an important consideration and even limitation of this method, that you have to know the extent of the input, and the extent of the input should be smaller than the extent of the output, so that you don't get overfitting. Okay. Does that answer your question?
Rows than columns.
Hmm.
So if we get a matrix where we have more columns than rows, then
That's a very different problem, and will not solve it right now. That's called minimum norm estimation, which we will not do right now. Don't use this method if that's going to happen. There are other techniques you can attempt, but we are not going there. And in this course, we'll not do minimum norm estimation in this course at all. You have to do something called regularization for that, which we will not do. Okay, let's try to understand this matrix F transpose F here. F transpose F is what? Is this -2, 1, 6, 0, 0, 0, 0, -2, 1, 6, 0, 0, 0, 0, -2, 1, 6, 0, 0, 0, 0, -2, 1, 6 is F transpose, and that collapses with this -2, 1, 6, 0, 0, 0. Calculate this first of all. What will be the size of the matrix? 4 by 4, okay. And what will be the entries in the matrix? For example, what will be this first entry here? 41, okay. 37, yeah, okay. 41. Okay. What about this? This entry here, 2, 2. Again 41. What about this entry? 41, 41. Okay. What about this entry here? This entry here. I don't think it's 0. What? No, let's be careful with it. 4. I am also going with 4. 4? Agreed? 4. What about this entry here? You see it? This entry will be 4. What about this entry here? Second row, first column. 4. Agreed? What about this entry here? -12, correct? Agreed? This entry here, -12. This entry here, -12. This entry here, -12. And these are zeros. Okay? This matrix is a matrix which has got some interesting special properties. Okay? It's a square matrix, right? It's a Toeplitz matrix, correct? It's a symmetric matrix. The reason I am saying is that this is two things. First of all, you can calculate these entries very fast. If you calculate just one column, then all the other numbers will be known. Do you see that? If you just calculate one column, then all of these, just by pulling the diagonal, you get all of these, and then this row, the numbers are going to be the same as the column, and then you pull the diagonals again, you get all the other entries, which means just calculating one column gives you all the entries. Okay? It also turns out, and we will not prove this, but it also turns out that this special structure of a matrix makes it amenable to fast inverse methods. So, you can get faster inverse methodologies for such matrices than you can get for general matrices, which is not something we might do it at the end of this lecture series, but probably not. Okay. What are these numbers? What are these numbers? Can we talk about these numbers, the 41 and the 4 and so forth, in terms of f itself? Yeah, the numbers are the numbers in the cross correlation sequence of f with itself. Right? Dot product of -216 with all delayed versions of -216 or whatever. Whatever is your impulse response with all delayed versions of the same impulse response. Are these numbers, and they are going on this, are these numbers and they are then being Toeplitzized. Okay? The cross correlation of a sequence with itself is called the autocorrelation of a sequence. Write that. And so now your methodology, we are learning to do it faster. You have that impulse response f, find the autocorrelation sequence of f with itself, which is just the autocorrelation sequence of f, populate your square matrix with numbers populated correctly, and then solve a set of linear equations with that square matrix as your coefficients, and then this is what? This f transpose x is what? This f transpose here. Just look at it. F transpose operating on x. What is that? That's the cross correlation of f and x. Do you get it? Do you get it? Right? So your technology now basically becomes that the best R is autocorrelation inverse operating on cross correlation. Which is nothing but an extreme big brother of u dot x upon u dot u. Okay. Cross terms upon same terms has now become autocorrelation inverse cross correlation. Finally, remember that if instead of the problem being expressed in this manner, that you know the impulse response, you know the output, you don't know the input. If the problem had been expressed in this alternative manner, that you know the input, you know the output, you don't know the impulse response. The way to solve that would be exactly the same. Why? Because of commutativity of convolution, You can think of the impulse response as the input and the input as the impulse response. So use the exact same technology that we developed to solve that problem, and that's got a different name. It's called system identification or optimal system identification, which is I gave you the input signal, I gave you the output signal, I ask you what convolution must have taken place. And by commodity of convolution, that turns out to be mathematically exactly the same problem. Okay, so today we saw the linear algebra of pseudo-inverse and how to use that for optimal deconvolution and optimal system identification. We are going to start doing very interesting things based on the pseudo-inverse formula from the next lecture onwards. This is going to take us deep into, much deeper into understanding what convolution is and what are the very interesting things that it does to its input. The smudge turns out to be something very special, and that is something that we'll start discussing in the next lecture. Thank you very much. I will see you on next Thursday.